Hello everyone. Let us continue the second part of today's class. Okay. So problem 43. What is the simulated annealing? Solution. Because of time limitation, I do not plan to introduce it here. Okay. Excuse me. So problem 44, what is a level set? And problem 45, what is Robbins-Monroe algorithm? Okay, the solution are both, okay, because of time limitation, I do not plan to introduce it here. Okay, problem 46, what is least squares? Okay, it is a very important topic, so we need to spend some time on it. Okay, solution. Problem statement. The objective consists of adjusting the parameters of a model function to best fit a data set. A simple data set consists of n points. Data pairs xi, yi, where I is equal to 1 to n. Excuse me. Where xi is an independent variable and yi is a dependent variable whose value is found by observation. Okay, the model function has the form f of x beta, where m adjustable parameters are held in the vector beta. Okay, the goal is to find the parameter values for the model that best fits the data. Okay, but what is the meaning of best? Okay, we will explain it later. Okay, the fit of a model to a data point is measured by its residue, defined as the difference between the observed value of the dependent variable, okay, that is yi, and the value predicted by the model. Okay, so the residue Ri is equal to yi minus f of xi beta. The least squares method finds the optimum parameter values by minimizing the sum of squared residuals as it should be boldface. Okay, I will fix this problem later. Okay, S is equal to summation I is equal to 1 to n Ri squared. Excuse me. An example of a model in 2 dimensions is that of the straight line. Okay, denoting the y-intercept as beta 0 and the slope as beta 1, the model function is given by f of x beta is equal to beta 0 plus beta 1 times x. Okay, I think you should already learned the equation of a straight line, okay, in 2 dimensions when you are a junior high school student. So it is very easy for you. Okay, a data point may consist of more than one independent variable. For example, when fitting a plane to a set of height measurements, the plane is a function of 2 independent variables, x and z, say. In the most general case, there may be 1 or more independent variables and 1 or more dependent variables at each data point. Excuse me. Okay. Figure 29. Okay, let us see figure 29. Okay, in figure 29, the residuals are plotted against corresponding x values. Okay, the x-axis is are x values from 0.15 to 0.55. Okay, and in the y-axis, there are residuals from negative 5 to 4. Okay, and you can see that there are many black points on the plane or on the plot. Okay, the random fluctuations about Ri is equal to 0 indicate a linear model is appropriate. Okay, we can see that this line represents Ri is equal to 0. Okay. Okay, figure 29 is a residual plot illustrating random fluctuations about Ri is equal to 0, indicating that a linear model Yi is equal to alpha plus beta times xi plus ui is appropriate. Okay, ui is an independent random variable. Okay, if the residual points had some sort, that is some kind of a shape and were not randomly fluctuating, a linear model would not be appropriate. Okay, for example, if the residual plot had a parabolic shape as in figure 30. Okay, let us see figure 30. Okay, figure 30, the residuals are plotted against the corresponding x values. Okay, you can see that on the x-axis, there are x values from 0 to 1. And on the y-axis, there are residuals from negative 0.02 to 0.02. Okay, and again, there are many black points on the figure. The parabolic shape of the fluctuations about Ri is equal to 0 indicate a parabolic model is appropriate. Okay, here is the line Ri is equal to, excuse me. Okay, here is the line Ri is equal to 0, and you can see that this black points is about around a parabolic curve, okay, like this. Okay, a parabolic model Yi is equal to alpha plus beta times xi plus gamma times xi squared plus ui would be appropriate for the data. Excuse me. The residuals for a parabolic model can be calculated via Ri is equal to Yi minus alpha hat minus beta hat times xi minus gamma hat times xi squared. Okay, where alpha hat, beta hat, and gamma hat are estimated parameters of alpha, beta, and gamma, respectively. Excuse me. Okay, also the residuals may be weighted to take into account differences in the reliability of the measurements. Okay. Next, let us look at how to solve the least squares problem. The minimum of the sum of squares is found by setting the gradient to 0. Since the model contains m parameters, there are m gradient equations. Okay, so let us see a partial s over partial beta j. Okay, let us review what is s. Excuse me. Okay, in equation 49, we can see that s is equal to summation I is equal to 1 to n Ri squared. Okay, so partial s over partial beta j is equal to 2 times summation I Ri. Okay, and according to the chain rule, we need to multiply it by partial Ri over partial beta j, okay, which must be equal to 0, for j is equal to 1 to m. Excuse me. Okay, and since Ri is equal to yi minus f of xi beta, the gradient equations become, okay, originally this term is partial Ri over partial beta j. Okay, when calculate the partial derivative, okay, you can treat yi as a constant. Okay, so yi partial beta j is equal to 0 and it disappears. And the minus sign is moved in front of this equation. And then we have partial f of xi beta, okay, here, over partial beta j, okay, which must be equal to 0, where j is equal to 1 to m. Okay, excuse me. The gradient equations apply to all least squares problems. Each particular problem requires particular expressions for the model and its partial derivatives. Okay, let us look at the easier case, linear least squares. Okay, after we look at the linear least squares case, we will look at nonlinear least squares case, which is more difficult. Okay, a regression model is a linear one when the model comprises a linear combination of the parameters. That is, okay, f of x beta is equal to summation j is equal to 1 to m, beta j times phi j of x. Excuse me. Where the function phi j is a function of x. Okay, letting capital Xij be equal to phi j of small xi, and putting the independent and dependent variables in matrices x, capital X and capital Y respectively, we can compute the least squares in the following way. Note that D is the set of all data. Okay, so D is the data set. Okay, L of D beta is defined as y, the square of the absolute value of y minus x times beta. Okay, and we know that this is the vector norm. Okay, or you can say the Euclidean norm or two norm. Okay, they are the same thing. Okay, so the square of the norm of a vector is equal to the transpose of the vector multiplied by the vector again. Okay, so this equation is equal to y minus x times beta transpose times y minus x times beta. Okay, and then we can use the distribution law to expand this equation. Excuse me. Okay, after the expansion, we will have this equation. Okay, and how do we obtain this equation? Okay, let us check this equation turn by turn. Okay, first is y transpose times y, okay, which is equal to y transpose times y. Okay, the next term is y transpose times negative x times beta, which is negative y transpose times x times beta. Okay, the next is negative x beta transpose times y. Okay, because the x beta transpose, okay, the transpose is taken on x times beta. Okay, so according to a property of a matrix, okay, let me write down the property. Okay, let me write on the blackboard. Okay, again, because I do not have a blackboard with me, so I use the Microsoft Word instead. Okay, if we want to calculate the AB, okay, if we want to calculate the transpose of A times B, okay, then it is equal to B transpose excuse me, and then times A transpose. Okay, this equation, I think you should have learned this equation when you take the course linear algebra. Okay, so let us go back to the handout. Okay, so x beta together transpose is equal to, of course, there is a minus sign before that. Okay, is equal to beta transpose. Okay, and times x transpose. Okay, and times y. Okay, here. Okay, and finally negative x beta transpose times negative x beta, which is equal to positive. Okay, again we use this equation. Okay, and then we can get beta transpose times x transpose times x times beta. Okay, then we get equation 53. Excuse me. Okay, finding the minima can be achieved through setting the gradient of the loss. Okay, loss is the function L to 0 and solving for beta. Okay, so we can see that partial L of d beta over partial B. Okay, so first let us substitute equation 53 into here. Okay, and we will have it is equal this term, okay, is equal to partial y transpose y, okay, minus y transpose x beta, and then minus beta transpose x transpose y, and plus beta transpose x transpose x beta. Okay, and over partial b, partial beta. Okay, after some calculation, we will find that this equation is equal to, okay, minus 2 x transpose y plus 2 times x transpose times x times beta. Okay, so how do we get this equation? Okay, let us see the handout. Okay, so this is chapter 2, page 47. Okay, it is a problem. Okay, derive the second equality of equation 54 in the handout. Okay, so now we want to derive the second equality, okay, this equality, okay, in equation 55. Okay, solution. Excuse me. Okay, first we must know the dimension of the matrices. Okay, this should be boldface. Okay, matrices X, this should be capital X. Okay, and okay, and Y, and the vector, okay, beta. Okay, like this. Okay, so first let us see the matrix X and find the dimension of it. Okay, let us go back to the handout. Okay, the element of matrix X are Xij. Okay, where I is equal to, okay, let us find the values of I. Okay, here, okay, in equation 49, I is equal to, I is equal to 1 to n. Okay, and okay, let us go back to here. Okay, and next let us find the values of j. Okay, in equation 52, we can see that j is equal to 1 to m. Okay, excuse me. Okay, so we can know that Okay, it is 25 minutes. Let us take a break.